Alright, hello everybody, and welcome to the first IFT 372 online study session. As I'm just making a message here, please post in the YouTube chat if you are here and attending, just because I want to know who is here and how many people are going to be participating. And basically, just as I posted on in the discussion board and the hallway conversations, these study sessions generally are based around your questions, so I don't particularly have a schedule to look at. I think the focus is going to be the homework that's due this evening, so the week 2 homework. We'll probably start by looking at that, but then if anybody else has any other questions that come up over the course of the study session, then we can figure out there. Alright, it looks like Steven's here. Hello. And let me know if if you can't hear me or if it's too slow. Unfortunately, I am somewhat limited to the technology I can use since I am not at school, so I don't have my typical computer setup, but I'm hoping that what I have here will be sufficient. But I think we'll give it a couple minutes here. We'll give it like 5 minutes for people to show up. If anybody has any initial questions, we can start with that. But basically, as soon as you're ready and you have your questions, then we can get started. Okay, so Stephen's asking about the question, asking about the signal intelligence. I believe that question you are talking about is, let me pull it up here. Let me see, where are we? It's most likely the one asking about what parameter of the signal affects. Let me just pull it up here before I have to guess. It looks like it's question 2 of the additional questions. Which parameter of the intelligence signal causes frequency deviation or variation of the carrier? Do all these signals reside in time domain, frequency domain, or both domains simultaneously? So that's question 2 of the additional questions. Okay. So basically, Stephen's saying that it's the second part of that question that he's not so sure about. So let's take a look at that. Let's get rid of what we have here. So it's basically asking you if when we're talking about an intelligence signal that we're trying to transmit information on, the question's asking you, when we're talking about a basic signal, do we care about the time that it's in, the frequency that it's using, or both? So I have to do a rudimentary sketch here, but the easiest way to talk about it is, imagine we have a talk radio station or something that's, the information signal is just using our voice. So we're just talking into it and we're coding that information and broadcasting that. When I'm talking to you and we have basically a recording of my voice, do we care about what time we're looking at that signal in? Or do we care about what frequency that signal is using? Or do we care about both? And I'll draw an illustration here in a second, and that might make it a little bit clearer. Let's see. So, for example, if we imagine that this is our basic wave that we're looking at, Stephen's saying we care about both, and he's basically right there, and that's what I'm going to talk about here. Because if we have this is a signal that we're looking at, in order for us to be able to get the information out of here, we need to know two things. We need to know what time in the signal we're looking at and what frequency that is. Because imagine that I'm talking to you right now and this is the recording that we're using. You need to know, basically, it matters what time we're at because my message varies based on time. So if I say a sentence, if you take the first half, you're getting I say, and you take the last half, a sentence. So the time does matter because as time passes, the signal changes. But then the frequency also matters too, because as I'm speaking, sound is made up of different frequencies. So if you want the higher pitches, you need to get the higher frequency. If you want the higher pitches of my voice, you need to get the higher frequencies. If you want the lower pitches, you need the lower frequencies. So the signal basically resides in both the time domain and the frequency domain, because both of those things are necessary for us to be able to recover the signal. We need to recover the frequencies so we can actually hear the sound, and we need to know what time we're looking at so we can recover the parts of the signal that we need. So for 2, we're looking at basically the signals reside in both the time domain and the frequency domain simultaneously. Oops. There we go. Yeah, and it makes sense when you kind of think about what you're looking at in terms of the signals, but it's you don't always think about signals in that way. So it's a little abstract if you don't have that initial step, but all right, Stephen's one other question regarding the work. Alright, so Stephen's looking at problem 2.3. You can calculate the wavelength. I'm not sure what relative frequency means. Is this a ratio between values or simply the difference? Yeah, this one can definitely trip people up sometimes. So basically what you're looking at for the frequency difference is, it's pretty much like you said, it's the difference between the different frequencies of the notes. So if you calculate the C note, the frequency of the C note, the frequency of the D note, what's the difference between those two frequencies? So it'll just be the difference in hertz of the two frequencies. Let me pull up. Let me just double check what you have in that table to make sure that's right. But Yeah, so for example, what they give you in that table is they give you the note and then the frequency in hertz of that note. And so you're just looking at the difference in hertz between the different frequencies of the notes. And then you're doing the additional calculations of the wavelength. But it sounds like you have that part down. So for example, we'll just look at, I'll give you one value just to make sure it's clear. So we're looking at, if we look at the C and D notes, C is 264 and D is 297. And then the difference there is obviously a difference of 33. And so that would be the relative frequency is that D is 33 hertz higher than C. And then etc. for the rest of them. Steven says the wavelength is simply 330, which was given divided by the value. Not 100% sure what you're getting at there. Remember from one of the previous questions that in order to find wavelength, we need the relationship with frequency and the speed of light. So I think you might have just mixed up a term there when you're saying that. And I think that's just a typo. But I'll wait for you to clarify. Okay, I think you meant speed of sound there. Yeah, okay. Yeah, you meant speed of sound. So 330 is your speed of sound in this example. Yeah, you're good. So yeah, for that example for C, you're absolutely correct. You take the speed of sound, you divide it by the frequency of the particular note, and you can find the wavelength. And again, that relationship is what was talked about in one of the prior problems. Let me see. I think it might have been one of our review questions. Let me see. Where are we? Yeah, and so that addresses one of the previous questions, review question 2.4, which is asking for the relationship between wavelength, frequency, and speed. And so we're looking at the relationship where we have basically lambda or wavelength times frequency equals the speed at which the signal is traveling. And so let me write this down just so we can see it here. And again, this is just a little bit more explanation because this is using a concept from a prior problem. But what we're looking at is we have wavelength times frequency equals speed. That's the relationship that we're looking at. And so for this problem, for this application, we're trying to find the wavelength. So instead we need to do frequency and And again, this is just some basic algebra here where we do wavelength equals speed divided by frequency in order to solve for the wavelength. And so that's what Stephen's saying. We know the speed of sound was 330 equals 330, and then we just divide by the frequency of the note in order to get the wavelength of the note. And so that's what we're looking at for that problem. And that's also the relationship for 2.4, if you were confused about that. But I think Stephen's got it, but just in case anybody else needed help with that one, that's the relationship that you're looking at when you're talking about the wavelength, frequency, and the speed. Now, for radio waves, we typically use the speed of light, which is not 330 meters per second. But because we're talking about musical notes, we need to talk about the speed of sound instead. So that's one thing that you typically will be using speed of light, but in this case, we're using speed of sound. Alright, so now that we've addressed those, Stephen, if you have any other questions, we can... Okay, yes, great. Stephen asks about Nyquist and Shannon's formula. These are pretty important and they keep coming up. So let's see what question you have on them and hopefully we'll work it out. So Nyquist exists in a perfect world and says that basically channel capacity is twice the bandwidth. So yeah, essentially what Nyquist is saying, and let me pull up some of the slides here. Let me find the slides with Nyquist in it. So yeah, so what we're looking at for Nyquist bandwidth, let me clear out this space over here. So basically for Nyquist, we're talking about in binary signals. So when we just have ones and zeros, we have a situation where channel capacity equals 2 times the allocated bandwidth. And again, that's just for binary, which is not typically what we work in. But that's the formula that you would use to find the amount of digital data that can be sent in a given bandwidth. Is binary, so it's 1, 2, so it's twice the bandwidth. Now, if we're talking about a non-binary system, that's where we have to start looking at Nyquist, Shannon, and things like that. So again, non-binary system means we have multiple levels. So instead of 0 and 1, we're now looking at potentially 0, 1, 2, 3, 0, 1, 2, 3, 4, etc. Typically it's a power of 2, so it's typically 2 levels binary, 4, 8, 16, 32, 256, etc. It can get as large as you need, but that's what it's typically a power of 2. And so when we're talking about multi-level signaling, our formula then changes to C equals 2b log base 2 of m, where m is the number of levels that we're talking about. And that's assuming, that's not factoring in signal to noise ratio. That's just looking at, we have a number of levels that we're using to broadcast a message. We have a certain bandwidth that we're using for this system. What's the amount of data we can transmit? The amount of data that we can send in a given bandwidth with a given number of levels of transmission. If we want to talk about noise, so say we have a signal, we have a system where we know we have a bandwidth, but we also know the signal to noise ratio of that system. Then we have our other formula, the Shannon-Hartley, which is information rate equals the bandwidth log 2 of 1 plus SNR. And so that's basically the same formula, but with different information. Now we don't have multiple levels, or we don't care about the number of levels. We're purely looking at the information we can send based on the noise present in the system, because that's our limiting factor. We have a signal to noise ratio. We know there's so much noise existing for every signal, for every amount of power that we send, right? Signal to noise is a ratio. It's saying how much noise exists per power in the system. And that limits how much information we can send, because we can only send information so tight, tightly packed, I guess you could say, so dense. We're limited to how much information we can send because the noise will just overwhelm it. If we send too much information, the noise is going to make it indistinguishable from the signal. And so, honestly, we're not going to be worrying too much about C equals 2B, the most basic form, because we rarely have to deal with binary systems. It'll come up, but we're going to be using the other two forms of this formula a lot. And one of the most common ways that we use it, and one of the ways that people tend to get tripped up, is that you'll be given, so for an example of a problem that you'll see later, so say that we're given, we have a system, using, let's say, 8 levels with an SNR of, let's say, 10 dB. Let's just make it easy and say decimal 10. And a bandwidth of 50 kilohertz. And so that's, say, we'll be given this system, and then the very common question is, what is the limiting factor? What, I guess we'll phrase it this way, does SNR or levels limit our C? And so this is the question that you'll be getting a lot, which kind of applies both of these theories. So we have a system and we know that it's using 8 levels. We also know it's SNR and we know the bandwidth. But we're trying to figure out what is stopping us from having basically the maximum amount of broad transmission capacity that we have. And so this question is basically saying, okay, calculate it out using 2b log 2m, figure out what our capacity is based on the number of levels we're using, and then also calculate it out based on the SNR that we're using, and find whichever one is lower, whichever one is limiting our channel capacity. And so that one comes up a lot, and sometimes people are confused about what they need to do, but basically these are two ways to figure out how fast we can transmit. If we have both, then it's the lower one, right? Because the lower speed is what we're stuck with based on the variables that we're given. So if we did the math out and we found that this I is, I guess I could just do the math here. So for this case, we'll plug in all our values. So I equals, and who knows what the math is going to turn out like since I just threw these numbers together. 1 plus 10. And if I plug that in, we get 172, 971. 58, oops, dot 58. And then if I plug in the levels, if I do the math for the levels over here, we get 2 times 50,000 log 2 of 8. And so that gives us 300,000. And so just looking at these numbers here based on this example that I gave, that's good enough. Our information, or our SNR, is the limiting factor in this equation because our channel capacity here is 30,000 bits per second. And our information rate down here is only 172,971.58. And that would technically round down. So technically we wouldn't have that 58 there, right? Because it's bits per second and you can't have partial bits, but that doesn't matter because that's a small difference. And Steven's asking, so we use Nyquist to find the theoretical maximum? Yeah, that's correct. So we use, yeah, because there's other factors that can impact the rate, but given bandwidth and number of levels, or bandwidth and SNR, you're looking for the theoretically, given the number of levels or given the SNR, what is the maximum capacity of the channel of that system? Because in the real world, there's going to be other potential impacts on that number. It's not necessarily going to be as good as you'd like it to be, but this is a theoretical maximum of what you're given. And so Steven's just clarifying what he's seeing, what the example I just worked through. So for the example I gave, you're determining if the levels limit the capacity or the SNR limits it. And if the Nyquist was lower, you would need additional levels, and that's correct. So in this case, looking at the numbers we just calculated, in this system, if we wanted to increase our channel capacity, because right now we're limited to 172,000, if we wanted to increase that capacity, we would need to reduce the SNR. So we would need to make that 10 a smaller number. We would need to reduce that number, make the system stronger, have more signal for noise, and that would increase our ability to transmit information in the channel. And then, like Steven says, if our channel capacity was the limiting factor, so if this wasn't 300,000, if this was only 100,000, we would need to use more levels. We would need to increase the number of levels we use to make the number bigger. Or, sorry, I just realized what I was saying there. We would need to increase the number in here, right? We would need to make the signal to noise higher because we want to make signal to noise stronger. We want more signal per noise. So we wouldn't want to reduce the 10, we would want to increase the 10, sorry. And then same thing in here, we would want to increase the number of levels to make the number bigger. So we want to increase the signal to noise because, again, higher signal to noise is a good thing. We want more signal per noise, not less. And this example that I gave here is just the most common application of what we're going to be seeing. Maybe not the most common, but it's a fairly common application. And Steven's just clarifying what I was saying. Yeah, increased signal power, lower noise. So we want a higher signal to noise ratio because we want more signal per noise. And again, this is just a common way of doing it, and a lot of people are confused when they start seeing the levels, or they're trying to find which does SNR or levels limit the system. That'll be the typical way this question's asked, and you just have to apply these two different factors. And Steven's actually last point there, increased signal power and lower noise. Those are the two ways we can affect our SNR, right? We can either increase the strength of the signal, which means there's more signal per noise, or we reduce the amount of noise, which means there's less noise per signal. And either of those will increase our SNR. But that's not strictly necessary for this problem. It's just a theoretical of SNR, how it works, what it means. Alright, so if there's any other questions, Stephen, on either the week 2 homework or some of the prior homework or the quiz, we can look at that, since I think you're the only one going to be present for this one. I knew there wouldn't be a huge turnout today, but I wanted to get one done before, I wanted to get one done this week. And again, it will be Thursdays and Sundays going forward, so I think the Thursday one was by far more popular than the Sunday. So Thursday 7 to 8 will be, I think, a higher turnout. It didn't come together this week to do it that day. But I figured having one on Sunday would be nice, just so we could get these last minute questions in before the homework is due. If possible, can you tell us what the quiz will cover? Yeah, we can take a look at, I'll just generally give you kind of an outline on it. I'm not going to obviously break through the specifics, but I can give you a general idea of what you're going to be looking at. Let's see. Let me just pull it up. This is going to be a second. Generally, for the quizzes, I'm just waiting for it to load. Again, I'm fairly limited by technology here, so everything takes a little bit longer than it should. But generally, the quizzes are going to be looking at more application, so it's going to be mostly the equations that you cover would be a good focus to look at. It's less of the review stuff that's mostly reserved for homework, just to make sure you're coming across and understanding these concepts as you find them. So I would definitely look at the equations that you cover in this section and just make sure, like we just did for the Shannon-Hartley, look at that. Look at the relationship between frequency and wavelength. Alright, come on. Because generally those equation questions make for better quiz questions than conceptual questions do. But let me see if I can get a little bit more information about the quiz here. And hopefully you didn't have any problems with the lockdown browser. It sounds like some people were having occasional issues, but hopefully it wasn't too bad. Alright, let's see what we have here. So just looking at generally you'll have a couple, so there are a couple conceptual questions on this quiz, basically looking at FM, AM. So basically you're given an FM thing with this bandwidth. Can you figure out, let me pull this up. So there's a little bit covering FM and AM, just the basics. Let me see if there's a lecture that has that information that I can look at. This is very slow. This Shannon Hartley, so what we were just talking about, calculating using either C equals 2b log 2m or information rate b log 2 1 plus SNR. So there's definitely some of that. And again, that's going to be a recurring concept, so you definitely want to make sure you have that. What else? And then some stuff addressing the noise temperature. So when we were looking at in some of the slides, we're talking about, let me see which lecture that's. So stuff out of like lecture 3.3, talking about noise figure and noise temperature. EB over N0, that sort of thing. So again, less of the, let me pull up, so less of the homework questions, like less of the, what parameter of the intelligence signal, but generally some more direct applications, so using formulas to figure out things. That's about as specific as I can get without getting too on the nose. But that would probably be the couple the things I would focus on is Nyquist and Shannon Hartley, FM, AM, and how to calculate basically like the bandwidth of those, noise, things like that. So Stephen, just clarifying that we do need to know noise figure. Generally, you don't need to get too much in detail about EB over N0, but knowing noise figure and how it relates and basically what it represents it will be useful. So mostly it's going to be looking at like, this was a problem with some of the other classes too, that a lot of people, this was a noise and N0 was a struggle, was definitely a topic that people struggled with. But I would look at, which slide is this? Slide 1, or yeah, I guess the first information slide of lecture 3.3, so technically page 2 of the PDF. But week 2, lecture 3.3, the slide that's entitled receiver noise level, that slide has everything you need in it, but it may take you a while to read through it and parse it and really understand what you're talking about. so what it's talking about, because it's a little tricky in the way it's laid out, and it's not exactly 100% clear on how everything relates. But I would definitely look at that receiver noise level slide. So again, it's slide 2 of lecture 3.3. That has everything you would need for noise on it. Feel free to email me if you don't understand a particular aspect of it, but that should have everything you would need for noise figure going forward. Just looking at noise figure, so for example on that slide it has NF dB equals 10 log 10 1 plus TE over 290, which is important because that relationship comes up again. And then it's also talking about noise power and Boltzmann's constant, and so that has all the fundamental calculations you'll need are on that particular slide. So I would definitely review that, and basically just understanding that, hey, noise figure, noise factor are basically 10 log 10 1 plus TE over 290, and that allows you to figure out the effective temperature, effective noise temperature of the device, looking at the thermal noise power level of the device. Some of that will come back later, some of that's useful now. Definitely look at that slide because that has a lot of information about noise on it. And Dr. Helm may have gone over that in his lecture this week. I haven't seen his lecture, but there's a lot of information on that slide. So I would be I'm not 100% sure how his lectures are structured, but if he went over his slides, that would be a good one to cover on your own if he did not as well. There's a little more discussion about equivalent noise temperature on slide 9 of that same lecture as well. But yeah, I've got time for another question, please. Wait, it's scheduled until 11, and that's a little flexible, but yeah, please. All right, 212 Part B. Okay, so yeah, 212 Part B, it's asking, let me get the exact wording of that, but I know, yeah, I know a lot of people have some issues with that one. So 212 is asking you to find given the narrow usable bandwidth of a telephone transmission facility, a nominal SNR 56 dB, 400,000, and a distortion level of less than 0.2%. Part A is what is the theoretical maximum channel capacity of traditional telephone lines. So again, that's what we're talking about. You're just using the SNR like we calculated here, or actually we're using the SNR. Yeah, because they don't give us levels, so we're just using the SNR to find theoretical maximum channel capacity. But then part B, which is what Steven's talking about, is what is the actual maximum channel capacity, and you don't actually need to worry about calculating it specifically. We're just looking for you to explain how the actual capacity would differ from the theoretical maximum. So it's like what we were talking about earlier, is that these numbers here are the theoretical maximum, but this question is asking you to say, okay, well, that's the theoretical maximum. How does the actual maximum relate to that? So in reality, how is our channel capacity going to relate to these theoretical maximums? You don't actually need to calculate the specific maximum channel capacity, if that makes sense. So basically just demonstrate that you understand how why the actual capacity is different from the theoretical maximum that we calculate here. So what other, why is there a difference, and what would that difference be? So we're not necessarily looking for a set number, just basically looking for what's the difference and why is there a difference. And so one of the main things, I guess I'll give you a push in the right direction, is that the question tells you that there's distortion involved. And what effect does distortion have on our ability to transmit information? So that's all that's really saying. Basically, as long as you realize that it's a theoretical maximum is what we're calculating. Yeah, Stephen, and that's a good catch on that one, because that also trips people up a lot, is that they have no idea what that. I think the book just says given the narrow bandwidth, but yes, you're right. It's 3 kilohertz. And again, we only need 3 kilohertz for telephone because that gets enough of voice to be recognizable. So it's basically that's after some testing they figured out that 3 kilohertz is enough to transmit the human voice effectively for a telephone call. So of course you're not going to be performing music over a telephone, or not particularly high quality music anyway, but it's enough to get enough voice is recovered to be understandable. All right. Well, do you have any other questions on any of the quizzes or anything like that? So it seems like you have the homework mostly under control. Reason for the wider bandwidth of FM than AM. Okay. Yeah, this is a good one to cover briefly. So yeah, we'll just cover the last question you brought up, the reason for wider bandwidth of FM than AM. Let me see where the good resource of that one is. But basically, what you're looking at when you have an FM signal, let me see, there's a good slide that has this information, but I can never remember exactly where it is. Might just be in the book as well. But basically, what the problem is, or not necessarily the problem, but the thing you have to notice about FM versus AM is that basically where the energy is going, I guess you could say, and I'll draw out an illustration once I find what I'm looking for. Where is it? Sorry, 1 second. I'm just trying to find the good illustration that I know is in here. Let me see. Yeah, and that's looking at the equation. Stephen just says he knows that AM requires 2B and FM requires 2B plus 2 delta F. Okay, it's in chapter 7, so that's why I wasn't seeing it. The main thing that you basically, for what we're saying about this, is when we're looking at AM, here, let me clear out what we have already. When we look at an AM signal, we basically have the upper and lower side bands. So we have, let me see the best way to illustrate this. Basically for AM, it's like we were looking at before, and this is kind of what we were looking at for some of the spectrum stuff, is that we have a base carrier frequency. So we have a carrier, let's not do that, let's just type it out. We have FC here, which is a carrier frequency. And then we have these two upper and lower sidebands because we have an information signal, which basically, let's say information signal goes from 0 to 5 kilohertz. Let's say that, for example. And here we'll say FC equals 30 kilohertz. These are just example numbers. But then information signal. And so with these numbers, basically, we have our core frequency, our carrier frequency of 30 kilohertz, and then our wave basically goes out on either side plus or minus 5. So we have up here, it'll go to 35 kilohertz, and down here, it'll go to 25 kilohertz. And so that's basically what we're looking at for AM, is it's just the addition of the two, of the information frequencies to the carrier frequency. But then what happens with FM, and again, the page I'm looking at here, which might give a little bit more insight, is page 223 and 224 of the text. Talks about kind of the differences between AM, FM, and PM. So that might be the best way, that's where I'm looking at to get this kind of explanation. And so that's, the book basically says, because of this, you're looking at your bandwidth of transmission is 2 times the bandwidth of the I guess 2 times the bandwidth of the information signal. But then for FM, or angle modulation in general, I guess, FM and PM, you have a lot more frequencies involved. And so, again, this is how, depending on how deep you want to go into the mathematics of it, you don't necessarily need to go in that deep, but essentially you have, in an FM system, you essentially have infinite sidebands. It's just with decreasing power as you go. So in FM system, you have your core carrier frequency here. And then you have, let me just draw out lines. And so you have plus the modulating frequency, so we'll say here, but then you have plus 2 times the modulating frequency, and then plus 4 times, and so you're essentially infinitely going outwards, but with less power at each frequency hop. And again, as far as getting into exactly why that happens, that's something you can look up on your own and get the math of it if you need that detailed explanation. But I think the book is all right. And that's got the formula in there that you were talking about, BT equals 2 delta F plus 2B. And Carson's rule talks about that too. But that's the general explanation of what's going on, is that your number of sidebands is much higher. Well, technically it's infinite in FM. AM, you just have plus or minus the information, the highest information frequency, the highest frequency component of the information. But then with FM, or phase modulation, angle modulation in general, you have infinite numbers of sidebands just with decreasing power. And that's all we're not necessarily looking for a mathematical proof of why that happens. It's basically just talking about, you can limit your conversation to the sidebands and be pretty much sufficient with your explanation on that one. So just AM, you have plus or minus the highest frequency component of this information signal, but then FM, you have infinite numbers of sidebands just with decreasing power. But each of those sidebands does carry information. So that's about, again, the book you can look at some of the math and you can go far too deep on some of this to figure out, okay, exactly why or how does this work if you need if you need all of the details in their full glory. But I think 224, page 224, 223 are basically going to be about the amount of the explanation you need. Alright, so that seems to be all the questions Stephen has, and he's the only one here. So we'll wrap it up now. Again, please email me with any questions that come up. If I'm unfortunately not going to be able to respond to anything probably before the homework's due today. I'm going to be busy most of today, but I will try to get back to you as soon as I can. If something else comes up, if you're looking at the week 3 stuff and you have a question, please email me. But yeah, all right. I think again this was the first study session. There will be another one Thursday of next week, 7 to 8, and I imagine that one will be a little bit more populated. I hope that one will be a little bit more populated. But hopefully this was useful, and good luck with the quiz and the homework tonight. All right, I think I will wrap it up there for today. Thank you for attending. Have a good day. Good luck with the homework and the quiz. All right. And again, actually, that's one thing I'll bring up is this recording will be available as soon as YouTube lets it go up on this channel. So I'll make a post on the discussion board to cover that as well. But if you come to this channel later, this video should be available for you to watch at some point tonight. I don't have any control over it. Once I hit upload, YouTube does all the processing on their end. But all right, that will be all. Thanks. Bye.